All right, today we are going to be talking about a fascinating topic called flux. And I hate to break it to you, but there's no such thing as a flux capacitor. And this is not going to help you figure out how to do time travel, because if it did, trust me, I would have done that back in the past. So, hate to break it to you, not so real. So, the question is, well, then what is flux? Okay, so flux is the amount of charge, and by charge, I should be lying, the amount of the E field, which is obviously created by charge, that interacts with a given surface. All right, so it's based on two things, the electric field and surface area. So the symbol for flux is a phi. And so since it is the electric field times the surface area, now that's a dot product. Okay, so let's talk about what that means. All right. So it's dot product. That means the electric field vector and the area vector must be parallel to each other. All right. So I'm not going to lie. This messes with my head, because if you were to say, well, Mr. Mansky, what's the area vector? So if I sketch this out here, like that's my surface, trying to do 3D. The area vector is defined by basically the face of that, and it's at a right angle to that. All right. So it tells us that the electric field vector, which we know that's a vector, no problem, and the area vector, which that one I still have my hard time wrap my brain around, must be parallel. But in reality, R-E-A-L-I-T-Y, there we go. But in reality, the electric field is perpendicular to the physical surface. So here, if I have an electric field that's pointing up, well, the electric field lines are parallel to the area vector, so these would match. And if you look, they're the ones that actually cross through the physical surface area that you're looking at. If I were to have an electric field line that was going this way, it would not be intersecting with that surface. It would go right alongside it. And it was also perpendicular to the vector representing the surface, so no flux. So here, our flux would be 0. And for these guys, our flux would be max. Like, well, if there's a max, is there also a min? Well, yeah, you go between a maximum, which is at a right angle, to 0, which is basically parallel. So what that means is that a lot of the electric field is usually not going to be at that, in one of these two cases. It's going to be somewhere in between. So what really happens more often than not is we have a surface that looks like that. The area vector looks like so, but the electric field is probably going to cross through at some angle. All right. So there's our electric field at some angle. Now, if we then look at this and we say this angle here between the electric field vector and the area vector is theta, then the only part that we care about would be this piece right here. And that would then be E cosine theta, because it would be the vertical piece, it would be this guy, so it would be adjacent to that angle, so we're going to be using cosine. So if we then take a step back, put it all together, this guy up here really ends up becoming phi, which is our flux, is equal to E dot A cosine of theta, where again, theta is the angle between En, the electric field vector, and the area vectors. All right. So that's our baseline. Now, what if this surface was not flat? Okay, what if the surface was changing? So therefore, the angle at which the lines were to hit that angle is going to then change, obviously, as well. So for that to be true, we then actually go to our fun friend, Mr. Integration. So we would then integrate the electric field dA, because the area over which it would cross through would become all changing constantly. All right. So we'll get into that a little later. Okay, we'll get into the integration part a little later. But what I want to do right now is just want to do a quick example to show you how this works mathematically. So if I sketch out just a random surface area, all right. So let's say I've got my surface, and there's my area vector. Let's do the electric field lines. I'm just going to draw a few, All right, there's my electric field lines. And now we actually put some numbers on this. Let's say that E is equal to 1,500 newtons per coulomb. All right, let's say this area here is basically a 10 centimeter by 10 centimeter square. All right. And the angle that's created, let's go with 60 degrees. So question could be, what is the flux? All right, what's the flux that's going to pass through this surface? So start with the equation for flux. Flux is E dot A. And this is pretty much straightforward plug and chug. So our E value is 1,500. Our area is the square, so that's 0.1 times 0.1. And then we'd have meters. Squares are units. So that's going to be 0.01. And then cosine of our angle between our area vector and our electric field vector is 60 degrees. So you can crunch your numbers and you get 7.5 Newton meters squared per coulomb. All right. And that'd be the size of your flux. Straight plug and chug, good to go. Now, the kicker with this is, as you've noticed, unless it is a flat, uniform surface that where everything hits that surface at the same angle, if it doesn't do that, we have to integrate. And so the question is where we go from there. So that'll be my next video. So you can check that out. Dude named Gauss did a lot of work with it. Aside from that, I think that's Flux in a nutshell. You guys have a great day, and I'll see you in class.